Right now, the universe is growing at a pace that defies everything our intuition tells us. Galaxies are drifting farther apart every second, yet they're not moving into some waiting void. There is no cosmic warehouse, no invisible boundary, no larger room surrounding the universe, and still space keeps expanding. Our minds instinctively look for a somewhere that's being filled, the same way air fills a balloon, or water spreads into an empty glass. But what if that idea simply doesn't apply to reality on a cosmic scale? What if the universe is not expanding into anything at all? Picture a balloon inflating in your living room. Its surface stretches outward because the air inside pushes against the surrounding air. There's space for it to grow into, but the universe plays by entirely different rules. When cosmologists say space is expanding, they don't mean it's pushing into a larger void. They mean the fabric of space itself is stretching everywhere at once. It's not the galaxies that are racing outward through emptiness. It's the emptiness itself, the stage on which everything exists, that is swelling, pulling everything apart without crossing into any external realm. This is one of the most profound and counterintuitive discoveries in science. It forces us to abandon the way we think about edges, boundaries, and outsides. There is no wall to break through, no cosmic border waiting beyond the stars. And yet this expansion is not abstract or invisible. We can observe its fingerprints imprinted across the universe, in the red glow of distant galaxies, in the stretching of ancient light, and in the quiet acceleration that's rewriting the fate of everything we know. Understanding this mystery begins with a simple but radical idea. Space doesn't need an outside to grow. It creates its own room as it expands. When astronomers talk about the expanding universe, they are not describing a cosmic explosion that flings matter into an empty void. There was no blast that sent galaxies hurtling through pre-existing space. Instead, space itself is stretching, carrying galaxies along like tiny markers embedded in a growing fabric. Imagine drawing a grid on a rubber sheet. If you pull the sheet in every direction, the lines get farther apart even though the dots on the sheet don't move relative to the material itself. This is what happens to galaxies. They are not travelling through the void. The void itself is expanding, increasing the distance between every point. This idea first emerged from real observations. In the early 20th century, astronomers noticed something strange. The light from distant galaxies was shifted toward the red end of the spectrum. This redshift wasn't caused by the galaxies speeding through space like race cars on a track. It was the light itself being stretched as it travelled through expanding space. That discovery shattered the long-held belief in a static, eternal cosmos. The universe is dynamic. The fabric of reality grows with time, and unlike an explosion with a clear centre, this stretching has no preferred location. From every galaxy's perspective, all others appear to be moving away. Every observer sits at the apparent centre of expansion, not because they are special, but because expansion is happening everywhere at once. This is why the balloon analogy works so well. Each dot on the balloon sees all the others drifting away as the surface grows, even though none of them is actually moving across the surface itself. Now replace the two-dimensional surface of the balloon with the three dimensions of our universe. That is the stage we live on. The unsettling truth is that there is no edge racing outward through darkness. There is no border to chase. There is only the fabric of space growing larger, taking everything with it. This realization marked a turning point in human understanding the moment we stopped imagining the universe as a thing inside something, and began to see it as everything there is. The most convincing proof that space itself is stretching comes from light. When a distant galaxy sends its light toward us, that light carries a clear signature, a pattern of wavelengths that tells us its original colour. But by the time it arrives, the pattern has changed. The waves are stretched, lengthened like ripples pulled across a widening pond. This effect is called cosmological redshift. It doesn't happen because the galaxy is racing away through space like a siren changing pitch. It happens because the space between us and that galaxy has expanded during the light's journey. Every wave of light gets pulled longer as the cosmic fabric beneath it stretches. That stretching turns brilliant blue and white starlight into faint red glows. Radiation that once burned in ultraviolet reaches us as gentle infrared. Light from the most distant galaxies has been stretched dozens of times over a silent record of the universe's growth etched into its wavelength. In the 1920s, this invisible stretching became visible through data. Edwin Hubble measured the redshift of galaxies and compared it to their distances. The farther away the galaxy, the greater the redshift. It was a perfect pattern. Something was increasing the distance between every galaxy over time, and that something was space itself. This discovery overturned the idea of a static universe. It revealed a cosmos in motion, expanding on a scale so vast that no single point can be considered its center. From our perspective, everything is moving away. From every other galaxy, the same view appears. This universal pattern is why scientists no longer speak of galaxies flying through space, but rather of galaxies being carried apart by the expansion of space. It's not motion in the ordinary sense. It's the slow breathing of the cosmos itself recorded in the reddening light of the distant past. Every night when you step outside and look up, it feels like you're seeing the universe in its entirety, a vast black ocean scattered with stars. But what you're really seeing is a small fragile bubble carved out by light and time. Light moves fast, but not infinitely fast. It takes 8 minutes to travel from the sun to Earth over 4 years, to reach us from the nearest star, and millions of years to arrive from the great spiral of the Andromeda Galaxy. That means everything you see in the night sky is a message from the past. The farther you look, the further back in time you're peering. But the universe has a finite age, about 13.8 billion years. That creates an invisible wall around us. Any galaxy farther than the distance light can travel since the beginning simply hasn't had time to send its light here. Beyond that limit, reality may continue forever, but it's cut off from us by time itself. And this is where expansion twists the knife. The galaxies that emitted their light billions of years ago are now far beyond the distance that light could travel in that time. By the time their ancient photons arrive at our telescopes, expansion has carried those galaxies to nearly 46 billion light-years away. This means we live inside what scientists call the observable universe, a finite bubble of visibility, surrounded by an unreachable beyond. It isn't made of walls or barriers of matter. It's made of the simple fact that light takes time to travel. No matter how powerful our telescopes become, there are regions of space whose light will never reach us. They exist, but they might as well not from our point of view. We are trapped inside a cosmic prison built not of stone or steel, but of time and light. The boundary of our observable universe is not the edge of reality. It's the edge of what light has had time to reach. Beyond it, the cosmos stretches on possibly without limit, but no signal, no photon, no whisper from that realm can ever cross the gulf that separates us. That gulf isn't made of empty space. It's made of time that simply hasn't passed yet. Think of standing in a dense fog at night. You can only see a small circle of ground around you. You know the world doesn't end at the edge of the fog, but everything beyond is hidden. The same is true for the universe. Our fog is cosmic time itself. Astronomers calculate that this fog currently encloses a sphere with a radius of roughly 46 billion light-years. Inside this bubble lie every galaxy we can ever observe, about 2 trillion of them. But beyond that horizon there could be billions or trillions more. They are just forever beyond reach. This is why it's misleading to picture the universe as a single glowing ball floating in darkness. The observable universe is not the whole story. It's a patch, a single illuminated bubble inside a much larger and possibly infinite ocean of reality. The strangest part is that the shape of this boundary isn't fixed. Each passing second, new light reaches us from ever more distant regions. The observable bubble grows by roughly 1 light second in radius every second. We see deeper into the past, into regions that were once hidden. even as the sources of that light drift farther away. What we call the universe is really just the part that fits inside our cosmic horizon. Everything beyond remains unseen, not because it doesn't exist, but because the rules of time and light simply won't allow us to look any further. There is a final wall to our vision, the oldest light in existence. It comes from a time long before galaxies, before stars, before even atoms could form. Astronomers call it the cosmic microwave background, the faint afterglow of the universe's birth. Around 380,000 years after the Big Bang, the cosmos underwent a quiet transformation. Until that moment, it was a seething plasma, blinding fog of particles and light. Photons scattered endlessly off charged particles. Light couldn't travel more than a few centimeters without being absorbed or deflected. The entire universe was opaque, like the inside of a star. But then the young universe cooled just enough for protons and electrons to combine into neutral hydrogen atoms. Suddenly the fog lifted. Photons were set free, racing in every direction. That ancient light has been travelling ever since, stretched by billions of years of expansion, reaching us now as a faint microwave signal. This light is everywhere. It comes from every direction at once, wrapping our world in a quiet glow invisible to our eyes but unmistakable to our instruments. Turn an old television to static and a tiny fraction of that fuzz is this very radiation, a remnant of the beginning. The cosmic microwave background marks the absolute edge of observation. We can never look past it. Anything that happened before those first photons escaped is hidden behind an opaque wall of plasma. It's like trying to see through the surface of the sun. That barrier isn't made of matter anymore, it's made of history itself. The light we receive today is a perfect snapshot of the universe, when it was just a glowing infant. It's our oldest cosmic record, the farthest our eyes and our instruments can ever reach. The cosmic microwave background draws the curtain on what we can see but not on what exists. Beyond that ancient wall, the universe may stretch on without end. If space is truly infinite, then what we observe is just one small patch, in a reality so vast that numbers themselves struggle to describe it. Infinity carries strange consequences. In a finite space, there are limited ways to arrange matter. But in an infinite cosmos, every possible arrangement must occur somewhere not once but endlessly. That means everything around you, from the stars above to the air you're breathing, could be mirrored in another distant region. Not metaphorically, but physically. The mathematics is clear. With infinite volume and finite particle configurations, repetition isn't a possibility, it's a certainty. Just as shuffling a deck of cards infinitely many times guarantees repeating sequences, an infinite universe guarantees repeating structures. Somewhere unimaginably far away, another Earth may orbit another sun. Somewhere even farther, another version of you may be standing under another night sky wondering the same thing. This isn't mysticism. It's the straightforward implication of combining large-scale uniformity with infinite space. Observations show that on the biggest scales, the universe looks strikingly homogeneous. Galaxy clusters, cosmic filaments, and voids repeat their patterns like a colossal web stretched across eternity. Inside our observable bubble, there may be 2 trillion galaxies. Just beyond it, there may be 2 trillion more, and beyond those more still. The further the bubble expands, the more of this infinite structure we glimpse. But infinity itself will always remain beyond reach. The idea of a repeating cosmos doesn't make our place smaller. It makes it part of a grander structure, an endless, self-similar fabric that extends in every direction. We are not at the center of anything. We are simply inside one repeating tile of an infinite cosmic mosaic. Long before stars and galaxies existed, the universe experienced its most violent growth spurt. In a fraction of a second, space itself ballooned from a subatomic size to something vastly larger than the observable universe today. This event is known as cosmic inflation, and it rewrote the structure of everything that would ever exist. Unlike ordinary expansion, inflation wasn't gradual. It was exponential. Imagine a single grain of sand suddenly swelling to a size larger than the entire visible cosmos before the blink of an eye. Nothing travelled faster than light, instead space itself expanded faster than light could cross it. Distances doubled and redoubled at a breathtaking rate, leaving once connected regions forever isolated. Inflation solved a deep puzzle. Without it, distant parts of the universe should look wildly different. They were too far apart to ever exchange light or heat. So why is the cosmic microwave background so smooth everywhere? Inflation stretched out any early irregularities, ironing the young cosmos flat and uniform. But it did something else too. Quantum fluctuations, tiny random ripples in energy at the smaller scales, were blown up to cosmic proportions during inflation. Those microscopic wrinkles became the seeds of everything. Galaxies, stars, planets, and eventually us. Inflation wasn't a simple burst that ended cleanly. The equations suggest it could be eternal, with new regions of space undergoing runaway expansion even now. Our observable universe may be just one pocket in a much larger inflationary landscape, a bubble adrift in an endless cosmic foam. This vision of reality is unsettling, but it fits the data with uncanny precision. The smoothness of the cosmic microwave background and the vast uniformity of space both point back to this extraordinary moment when the universe was barely born and yet already unimaginably large. If inflation can begin, it may never truly stop. While one region of space slows down and cools into a universe like ours, other regions keep expanding at breakneck speed. Tiny quantum fluctuations can trigger new bursts of inflation, each one budding off into its own separate bubble universe. This endless process is called eternal inflation. In this picture, what we call the universe is only one bubble floating in a vast inflating sea. Around us, far beyond the edges of our observable horizon, other bubbles may be forming right now, countless newborn universes expanding into their own isolated domains. Each bubble is causally cut off from the others. No light can ever cross the gulf between them. And here's where things become truly strange. The physical laws inside each bubble may not be identical. Tiny differences in the underlying quantum fields can create entirely different realities. In some bubbles, stars and galaxies may form much as they did here. In others, the forces of nature could be too weak or too strong for matter to assemble. Most would be sterile, dark, and silent. A few by pure chance might cradle life. This concept isn't science fiction. It's the direct mathematical consequence of the same equations that explain the smoothness of the early cosmos. If we accept inflation, then the multiverse follows naturally, an infinite froth of bubble universes, each with its own history, its own fate, and perhaps its own observers asking the same questions we do. We may never detect these other universes directly. They lie forever beyond our cosmic horizon, but their existence could explain why our universe seems so perfectly tuned for stars, planets, and life. We live in a bubble where the conditions happen to allow it, not because it was designed that way, but because only bubbles like this can ever ask the question why. We experience space as three-dimensional. We can move left or right, forward or backward, up or down. It feels complete, but physics may tell a different story. Some of the most ambitious theories suggest our familiar three dimensions are only a small part of a far richer structure. Hidden beyond our perception could be extra dimensions curled up so tightly that even particles can't detect them. To imagine this picture: an ant walking along a garden hose. From the ant's point of view, the hose seems like a one-dimensional line, but in reality it's a cylinder. The ant could also crawl around its circular surface, a direction invisible to someone watching from far away. The universe may be like that hose, three dimensions large enough to notice and others compacted too small to see. This idea leads to a bold picture called the brain world model. In it, our universe is a three-dimensional membrane, a brain floating in a higher dimensional space known as the bulk. All the familiar particles and forces are trapped on our brain, unable to escape into the extra dimensions, all except one: gravity. This could explain why gravity is so weak compared to other forces. While light and matter are confined, gravity may leak into the higher dimensional bulk, spreading its influence thinly across multiple dimensions. The expansion we observe might be our brain stretching inside this larger hyperspace. And if extra dimensions exist, there could be other brains too. Parallel universes lying just a tiny distance away in directions we can't point to. These neighbouring brains could be so close that their gravity occasionally tugs on ours, or they could remain forever isolated. In this view, the universe isn't expanding into nothing. It's expanding into higher dimensional space we can't perceive, a hidden stage upon which our entire cosmic story unfolds. Even if extra dimensions never reveal themselves, the shape of the space we live in can already dissolve the question. What is the universe expanding into? The geometry of the cosmos determines how expansion behaves, and in some shapes, talking about an outside simply doesn't make sense. General relativity allows three broad possibilities. Space can be flat, like an infinite sheet of paper, curved like the surface of a sphere, or saddle-shaped with negative curvature. Observations suggest our universe is almost perfectly flat. But flat does not necessarily mean infinite. You can take a flat sheet, roll it into a cylinder, or join its edges to make a donut shape. Locally it still feels flat, but globally it loops back on itself. If our universe has this kind of topology, travelling in a straight line long enough could eventually bring you back to your starting point. There would be no boundary to cross, only a smooth, self-contained space. In a donut universe, expansion isn't about pushing outward into some external void. It's simply the donut itself growing thicker, its surface area increasing without invading anything beyond. Astronomers have searched for repeating patterns in the cosmic microwave background that might hint at such a wrapped geometry. So far, no definite signs have been found. That may mean our universe is larger than the scale we can observe, or its shape is more subtle than our instruments can detect. But the key insight stands: an expanding space doesn't need an external container. If the universe wraps around itself, expansion is not movement into a bigger room. It's a stretching of the room's own walls that have no outside. When space expands, time is stretched along with it. This is not just a poetic idea, it's a measurable reality. Every second that passes in the far reaches of the cosmos doesn't flow the same way it does here. Expansion doesn't only separate galaxies in space, it separates their experience of time. Imagine watching a distant supernova through a telescope. Its light reaches us after billions of years, carrying not only colour and brightness, but also timing. The explosion appears to unfold in slow motion. Days stretch into weeks, weeks into months. This isn't because the star itself explodes more slowly, but because the space its light crosses is expanding, stretching the intervals between each wave of light. This effect, known as cosmological time dilation, grows more dramatic with distance. A galaxy at the edge of our observable universe seems to experience time flowing roughly 10 times slower than we do. Its clocks and everything that happens there appear to tick more gently, as if caught in a slow current. This leads to a profound consequence. There is no single universal now that spans the cosmos. What we call the present moment is local. Observers in distant galaxies define their own present, shaped by their own position in expanding space-time. As the universe accelerates, this divergence grows sharper. Faraway regions will seem to freeze in time, their light stretched to near infinite wavelengths. Future civilizations may look outward and see a sky where distant galaxies appear almost motionless, trapped in an ever-slowing cosmic film. Expansion, then, is not only rewriting the structure of space, it is reshaping the flow of time itself, bending the very rhythm by which the universe ages. Cosmic expansion is not just something happening now, it is the engine driving the ultimate fate of everything. If the current acceleration continues, the distant future will be cold, dark, and silent. Stars will fade. Galaxies will vanish from view, and the universe will enter an era where nothing new can ever happen. In roughly 100 billion years, the last light from distant galaxies will slip beyond our cosmic horizon. Expansion will carry them away faster than their light can reach us. To observers of the far future, the universe will appear to contain only the galaxies of our local group. A tiny island surrounded by an infinite black ocean. All evidence of cosmic expansion will be gone, but the stars themselves will not last forever. In trillions of years, every star will exhaust its fuel. The sky will grow darker as stellar nurseries fall silent. Gravity will no longer have enough raw material to form new suns. The universe will drift into what physicists call the degenerate era, a time ruled by cold stellar remnants. Even those remnants won't endure forever. Over unimaginable spans of time, atoms themselves will begin to decay. Protons, the building blocks of matter, are expected to fall apart after a period so long that our current age is a mere flicker in comparison. When that happens, planets, stars and galaxies will dissolve into a thin mist of elementary particles. Expansion ensures that this mist will spread thinner and thinner. Energy will flatten out, temperature will sink toward absolute zero, and time itself will lose any trace of drama. No stars, no structure, no heat, only a silent, endless night. Long after the stars have faded and the galaxies have dissolved, only black holes will remain as the dominant architects of the cosmos. These ancient giants, forged in the collapse of massive stars or lurking at the centers of galaxies, will outlive everything else. For trillions upon trillions of years, they will be the last significant sources of energy in an ever-cooling universe. But even black holes are not eternal. According to Hawking radiation, they slowly evaporate by emitting tiny amounts of energy over time. The smaller the black hole, the faster this process happens. Stellar mass black holes will take far longer than the current age of the universe to vanish completely. Supermassive black holes at galactic centers will endure even longer surviving, until roughly 10 to the power of 100 years into the future. During this age, the universe will be a strange and nearly empty place. The night sky will hold no stars, no glowing galaxies, only isolated black holes scattered across expanding darkness. These silent objects will slowly leak their mass away as faint radiation, like fading embers in an infinite void. As each black hole evaporates, the universe loses its last sources of concentrated energy. What remains is a thin uniform sea of low-energy photons, neutrinos, and other elementary particles drifting endlessly apart. Expansion will keep stretching this cosmic fog, lowering its temperature closer and closer to absolute zero. This is the slow, quiet march toward heat. Death. A future where no process can extract energy. No new structure can form and no observer can exist to witness the end. It's not an explosive finale. It's the universe's long exhale into silence. Not all endings are quiet. If dark energy doesn't remain constant but grows stronger over time, the universe may not drift toward a cold sleep. Instead, it could end in violence, a catastrophic unraveling called the Big Rip. In this scenario, expansion doesn't merely accelerate. It becomes overwhelming. Gravity, which binds galaxies together, grows weaker compared to the repulsive push of dark energy. Eventually, space itself stretches so fast that no force can keep anything intact. Billions of years from now, galaxy clusters would be the first to break apart. The vast gravitational webs connecting galaxies would snap, leaving each one to drift alone. Hundreds of millions of years later, the galaxies themselves would be torn apart as expansion rips stars away from their spiral homes. When the universe is just minutes from its end, the solar system would disintegrate. Planets would be flung into the dark as the sun drifts away, no longer able to hold its children in orbit. Then, in the final seconds, expansion would overwhelm the electromagnetic forces that hold matter together. Atoms themselves would unravel, nuclei would split, and the fabric of space-time would stretch to its breaking point. The laws of physics as we know them would cease to operate. The timeline of this destruction depends on how dark energy behaves, something we still don't fully understand. It could be tens of billions of years away. or never happen at all. But if it does, the big rip would not be a slow fading like heat death. It would be the ultimate rupture, the universe tearing itself apart from the inside out. When we imagine empty space, we picture nothingness, a perfect silent void. But modern physics has revealed a far stranger truth. Even in the darkest regions between galaxies, space is anything but empty. It seethes with invisible activity, a restless ocean known as the quantum vacuum. On unimaginably small scales, particles and antiparticles flicker in and out of existence. They borrow energy from the vacuum, then annihilate each other in timeframes so short that no detector can catch them directly. This constant microscopic storm is called quantum fluctuation. These fluctuations are not just abstract theory. They produce measurable effects such as the Casimir effect, where two metal plates placed close together feel a real physical push caused by virtual particles being excluded between them. This is the pressure of the vacuum itself. And vacuum energy doesn't just sit there, it has weight. Unlike ordinary matter which pulls space together, vacuum energy creates a repulsive gravitational effect. The more space there is, the more vacuum energy appears and the faster expansion accelerates. It's a self-reinforcing engine. This strange property may explain the mysterious dark energy driving cosmic expansion. The fabric of reality is constantly generating space out of what looks like nothing. In a sense, the universe doesn't need an external fuel source. It expands by feeding on the vacuum itself. What seems like empty space is actually the raw foundation of the cosmos, a restless, invisible field capable of shaping the fate of everything that exists. The same vacuum that seems empty is in fact the universe's most powerful engine. While ordinary matter pulls space inward, vacuum energy pushes it apart. This is what makes dark energy so different from anything else we've ever observed. As the universe grows, more space comes into existence, and with each cubic meter of new space, the same amount of vacuum energy fills it. Unlike matter, which gets thinner as it spreads out, dark energy keeps its density constant. That means its total influence grows over time, slowly overtaking everything else. 5 billion years ago, the universe was still dominated by matter and radiation. Gravity was stronger than dark energy's push. Expansion was slowing down, but as galaxies drifted farther apart, their mutual pull weakened while vacuum energy remained steady. Eventually, the balance tipped. The expansion began to accelerate, and it hasn't stopped since. Today, dark energy makes up about 68% of the total energy content of the cosmos. Ordinary matter, everything in stars, planets, and gas clouds, contributes less than 5%. The rest is dark matter, invisible but gravitationally attractive. This dominance explains why expansion no longer needs a spark. The universe accelerates because vacuum energy naturally pushes it to do so. The more it expands, the more vacuum energy fills the growing space, creating an elegant but unsettling feedback loop. We still don't know exactly what dark energy is. It could be a property of the vacuum itself, or the effect of a new unknown field woven into space-time. But one thing is clear. This invisible force now controls the fate of the cosmos. The stars, galaxies, and even the large-scale structure of reality dance to the rhythm set by something we can't see. The story of cosmic expansion isn't built on speculation alone. It rests on evidence, real measurements taken across a century of astronomical discovery. The first clear clue came from Hubble's law, the relationship between a galaxy's distance and the redshift of its light. In the 1920s, Edwin Hubble observed that the farther a galaxy is from us, the faster it appears to be receding. He didn't find a few outliers, he found a perfect pattern. The light from nearby galaxies was only slightly redshifted, while the light from more distant galaxies was stretched dramatically. That meant the expansion wasn't random. It was orderly, universal, and measurable. This discovery turned cosmology from philosophy into science. For the first time, the size of the universe wasn't just guessed, it could be calculated. The slope of Hubble's graph became the Hubble constant, a number that encodes the current rate of expansion. Since then, astronomers have refined these measurements with extraordinary precision. By studying Type Ia supernova stellar explosions bright enough to be seen billions of light-years away, they confirmed that distant galaxies are moving away even faster than expected. Something more than gravity was at work. That something is what we now call dark energy. Today, multiple lines of evidence converge. Redshift surveys the pattern of the cosmic microwave background, and the distribution of galaxies all point to the same conclusion. Space itself is stretching. The universe is not static. It never was. Every photon that reaches our telescopes carries a piece of this story. By decoding its wavelength, astronomers can look back in time, reading the silent expansion written into the fabric of light itself. Measuring the scale of the cosmos is like trying to map a dark ocean with only a few distant lanterns to guide you. Fortunately, the universe provides its own beacons. Type Ia supernova. These stellar explosions shine with nearly uniform brightness, making them ideal, standard candles for measuring vast cosmic distances. A Type Ia supernova occurs when a dense white dwarf star steals material from a companion until it reaches a critical mass. At that point, a runaway thermonuclear reaction ignites, tearing the star apart in a brilliant flash. Each of these explosions releases roughly the same amount of energy, meaning their true brightness is well known. By comparing their intrinsic brightness to how dim they appear from Earth, astronomers can calculate their distance with remarkable accuracy, and by analyzing the redshift of their light, they can determine how fast the universe has expanded since the moment that light was emitted. In the late 1990s, two independent research teams used these cosmic lighthouses to probe deep into the universe's past. What they found was unexpected distant supernovae were dimmer than they should have been. The only explanation was that they were farther away than predicted by a slowing expansion. Something was pushing the universe to expand faster over time. That something was dark energy. This discovery was revolutionary. It showed that cosmic expansion is not just continuing, it's accelerating. The finding was so profound that it earned the 2011 Nobel Prize in Physics. Today, supernova measurements remain one of the cornerstones of modern cosmology. They allow us to trace the history of expansion with exquisite precision, transforming the night sky into a cosmic map stretching billions of years into the past. Long before telescopes could glimpse the most distant galaxies, the universe itself left behind a perfect record of its early state. That record is the cosmic microwave background, the faint afterglow of the Big Bang. But it's more than just ancient light. Hidden within its delicate temperature patterns is a cosmic fingerprint of how the universe has expanded over billions of years. When this light was released, the universe was a hot, dense plasma ringing with sound waves. Small fluctuations in density created pressure ripples that traveled through space like vibrations in a vast drum. When the cosmos cooled and became transparent, those ripples froze into the microwave background. Today, satellites like WMAP and Planck have mapped these tiny variations across the entire sky with extraordinary precision. Each subtle bump and dip in this map reveals how space has stretched since that ancient moment. It shows us the overall shape of the universe astonishingly flat, and gives us the ratio of dark energy, dark matter, and ordinary matter. It's like looking at a baby picture of the cosmos and being able to predict its entire life story. But the microwave background is only one piece of the puzzle. Astronomers also study the large-scale structure of galaxies, the cosmic web of clusters and voids that stretches across the universe. The patterns in this web match the ripples frozen in the early plasma. By comparing, the two scientists can track how expansion has changed over time with stunning accuracy. These independent lines of evidence all point to the same conclusion. The universe is expanding, and that expansion is accelerating. The cosmos has been keeping its own records for nearly 14 billion years, and now we've learned to read them. At the dawn of the 20th century, even the greatest minds believed the universe was fixed and eternal. Albert Einstein himself introduced the cosmological constant to his equations of general relativity. not because nature required it, but because he assumed the cosmos had to be static. His own mathematics hinted that space should either expand or contract. To stop it from doing either, he added a term to hold the universe in perfect balance. Meanwhile, astronomers were making quiet but profound discoveries. Observations of nebulae hinted that many were not clouds inside the Milky Way, but entire galaxies far beyond. The scale of the cosmos was already expanding in our minds before we realized space itself was doing the same. Then came Edwin Hubble. By measuring the redshift of these galaxies and their distances, he uncovered a simple but revolutionary pattern. The farther a galaxy is, the faster it seems to move away. In 1929, this became Hubble's law. The universe was not static. It was expanding. When Einstein heard of this discovery, he reportedly called the cosmological constant his greatest blunder. He had tried to hold back a truth his own theory already whispered. Ironically, decades later, that same constant or something, very much like it, would return as the leading explanation for dark energy. This moment marked a turning point in human understanding. For the first time, we saw the cosmos not as a silent, fixed backdrop, but as a living, dynamic structure. A fabric that stretches, grows, and evolves. The universe was breathing, and we had finally learned to listen. For decades after Edwin Hubble's discovery, cosmologists believed that the expansion of the universe must be slowing down. Gravity, they thought, would gradually pull everything back, either halting the expansion or reversing it entirely. The cosmological constant, Einstein's greatest blunder, was left behind as an abandoned relic. But the universe had a surprise in store. In the late 1990s, observations of distant Type Ia supernova revealed that expansion wasn't slowing at all. It was accelerating. Something was pushing the fabric of space outward with increasing strength. To explain this unexpected force, scientists revived Einstein's constant not as a blunder, but as the simplest explanation for dark energy. In Einstein's original equations, a positive cosmological constant acts as a repulsive pressure counteracting gravity. Now it seemed that the universe itself was powered by such a force. This was a profound reversal. What had once been an artificial patch added to keep the cosmos static became the leading candidate to explain why it expands faster and faster. Einstein had tried to hold the universe still, but his mathematics contained the very tool to describe its acceleration. Today, the cosmological constant remains one of the most elegant and mysterious ways to describe dark energy. It fits the observations beautifully, yet raises unsettling questions. Why does it have the value it does? Why isn't it zero or unimaginably large as quantum theory might suggest? The constant that Einstein once erased has returned as a cornerstone of modern cosmology. The universe, it seems, had the last word. We began with the simple, unsettling question: if nothing exists outside the universe, what is it expanding into? After exploring cosmic horizons, inflation, dark energy, and the shape of space-time, the answer is both elegant and profoundly counterintuitive. The universe isn't expanding into anything. It's expanding into itself. This is possible because space isn't a stage built inside some larger container. It is the container. It is the fabric that defines distance, direction, and time. When space expands, it doesn't push against a boundary. Instead, the distances between points grow as the fabric stretches everywhere at once. Think again of the balloon analogy, but with a twist. The surface of the balloon represents the universe. As it expands, no part of the surface moves into some external realm from the perspective of a creature living on that surface. The only thing that changes is the distance between points on the balloon itself. Our three-dimensional space behaves in the same way, only without a true outside. This perspective also explains why no galaxy sits at the center of expansion. Every point in space watches all the others drift away, not because anything is moving outward, but because the entire fabric is stretching uniformly. Expansion is not motion through space, it is the creation of more space. There is no cosmic wall ahead of us, no edge where space runs out, no larger void waiting to be filled. The universe is self-contained and its growth happens from within. It doesn't invade an external realm, it simply becomes larger. Once we let go of our everyday intuition and embrace this cosmic geometry, the question, what is it expanding into, dissolves. There was never an outside to begin with. The idea of an outside is a deeply human instinct. We live in a world full of walls, horizons, and borders. Every object we know exists somewhere in a larger space. A house sits on a street. A city sits on a continent. Even the Earth itself orbits within the vastness of space. So when we hear the word expanding, we automatically imagine something growing into something else. But the universe doesn't follow those rules. Space itself is not an object embedded in a larger arena. It is the arena. It doesn't need an exterior because it defines what where means. Asking what's outside the universe is like asking what's north of the North Pole. The question seems meaningful, but it breaks down once you understand the geometry. Our intuition struggles here because our brains evolved to navigate small bounded environments. We imagine boxes, shells, and containers, but on cosmic scales these mental shortcuts fail. The expansion of the universe doesn't create new territory beyond some border. It increases the distance between everything already inside. This is why cosmologists use mathematical tools like Friedman, Lemaitre, Robertson, Walker metric, rather than pictures of balloons in empty rooms. These equations describe how distances grow in a self-contained space-time. No outside is required, not even conceptually. It's a profound shift in perspective. Instead of seeing ourselves on a tiny island in a larger ocean, we begin to understand that the ocean is all there is. There is no shore to reach, no outer space beyond space. And once that clicks, the original question, what is the universe expanding into, reveals itself as a trick of language, not a mystery of nature. Over the past century, humanity has pieced together one of the most astonishing stories in science. What began as a simple observation, distant galaxies drifting away, revealed a universe that is dynamic, vast and stranger than anything our ancestors could have imagined. We now know that what expands is not matter, moving through a void, but the very fabric of space-time. Hubble's law showed that every galaxy sees every other galaxy recede because expansion happens everywhere at once. Cosmic microwave background gave us a baby picture of this process frozen in time. Observations of Type EIR supernova proved that this expansion is accelerating, driven by dark energy, a mysterious pressure woven into the vacuum itself. We've learned that our observable universe is just a small bubble in a much larger structure. Its boundary isn't physical but defined by the distance light has had time to travel. Beyond it, the cosmos may stretch forever, or it may loop back on itself like a cosmic donut. Its geometry may involve extra dimensions hidden from our senses. We've also glimpsed the future, galaxies slipping beyond reach, stars fading, black holes evaporating, and a universe drifting toward darkness. Whether it ends in a slow freeze or a violent Big Rip expansion will shape everything to come. And perhaps the most humbling revelation of all, the question of what lies outside the universe doesn't belong to nature but to the limits of human intuition. Space doesn't expand into anything. It expands because it is everything. This is the power of cosmology. It doesn't just tell us where we are, it rewrites what where even means. Cosmic inflation wasn't just a sudden stretching of space. It was also the moment when the tiniest quantum tremors were magnified into the grand architecture of the cosmos. During this ultra-brief epoch, fluctuations smaller than a single atom were blown up to cosmic scales, becoming the blueprint for every galaxy, every star, and eventually for us. Quantum fields are never perfectly still. Even in a vacuum, they ripple with quantum fluctuation. Under normal conditions, these fluctuations are microscopic and short-lived, but inflation changed the rules. As space expanded exponentially, it trapped these fluctuations, stretching them faster than they could collapse or disappear. The result was a frozen pattern of density differences, slightly denser regions surrounded by slightly emptier ones. Though tiny, these contrasts seeded the formation of everything. Over billions of years, gravity amplified them into clusters, filaments, and voids. The vast cosmic web we observe today. This is one of inflation's most remarkable predictions. A universe that looks uniform on large scales but carries delicate fingerprints of its quantum origin. When we map the cosmic microwave background, we're looking directly at those fingerprints. Every warm and cool patch in that faint afterglow is a fossilized quantum ripple. It means that the grandest structures in the cosmos galaxy, clusters spanning millions of light years, were born from fluctuations smaller than a proton. Inflation turned the chaos of quantum noise into the skeleton of the universe. If inflation truly happened, it should have left behind a signature not written in stone but in light. That signature lies hidden in the subtle temperature variations of the cosmic microwave background, the oldest light we can observe. When the Wilkinson Microwave Anisotropy Probe WMAP began mapping the sky in the early 2000s, it revealed a nearly uniform glow, but on closer inspection the data showed tiny fluctuations, just 1 part in 100,000. Those delicate ripples matched exactly what inflation theory predicted. Random scale invariant patterns imprinted by amplified quantum fluctuation. Later, the Planck satellite refined those measurements to exquisite precision. It confirmed that the universe is astonishingly flat, consistent with an inflationary beginning. It also measured the precise spectrum of those fluctuations, showing a slight tilt, exactly the kind inflation models expected. But the most dramatic clue inflation could leave behind is something even subtler. A swirl in the polarization of the microwave background called B-mode polarization. This would be direct evidence of primordial gravitational waves, ripples in spacetime generated during the inflationary burst. Detecting those B-modes has proven extremely difficult. A 2014 claim by BICEP 2 was later retracted when the signal turned out to be dust in our own galaxy. But the search continues with increasing sensitivity because finding them would be like hearing the echo of the universe's birth cry. Every warm and cool patch in the CMB isn't just random static. It's a fossilized record of the first fraction of a second the smoking gun of inflation etched across the entire sky. Cosmic inflation is one of the most powerful ideas in modern cosmology, yet it sits at a delicate boundary between theory and evidence. We have strong indirect clues like the flatness of the universe and the precise pattern of fluctuations in the cosmic microwave background, but no direct way to recreate or observe inflation itself. The reason is simple. Inflation happened at energies far beyond anything we can reach. To probe that epoch, we would need a particle accelerator trillions of times more powerful than anything humanity could build. The physics that drove this rapid expansion likely involved fields and forces that existed only during the first slivers of a second after the Big Bang. Our telescopes can't see beyond the cosmic horizon, and inflation itself pushed most of the universe permanently out of view. The evidence we rely on, temperature variations, polarization patterns, large-scale structure, is like listening to echoes in a cave long after the original sound has faded. Worse, multiple inflation models can produce nearly identical observational signatures. Even if we measure the sky with infinite precision, it might not be enough to pin down the exact mechanism that started it all. Some models involve a single inflaton field. Others propose entire landscapes of fields, each giving rise to different bubble universes. This is why inflation remains both a triumph and a mystery. It explains what we see with remarkable accuracy, but it also confronts us with questions that may never have a final testable answer. Inflation takes us to the very edge of what science can observe, and just beyond that edge lies the unknown. Cosmic inflation doesn't just explain why our universe looks the way it does. It also suggests something far more audacious, that our cosmos might not be the only one. In many inflation models, the process doesn't end everywhere at once. Some regions stop inflating and cool down, forming universes like ours. but elsewhere inflation keeps going. This never-ending process is called eternal inflation. It paints a picture of reality not as a single expanding bubble, but as an infinite froth of bubbles, each a separate universe with its own history. The region we call the universe is simply the one we inhabit, one bubble among countless others, floating in an ever-inflating sea. Inside each bubble, the laws of physics may look familiar, or they may be radically different. Tiny differences in initial conditions can alter the strength of fundamental forces, the masses of particles, even the number of spatial dimensions. Some bubbles might be lifeless and dark, collapsing as soon as they form. Others could host galaxies, stars, and observers asking the same questions we do. This isn't science fiction dressed in cosmic language. It's a natural mathematical consequence of inflationary dynamics. If space expands exponentially, most of it never stops. New bubble universes keep forming forever, each one causally isolated from the rest. No signal or spacecraft could ever bridge the gap between bubbles. The expansion between them is faster than light. The idea of the multiverse is controversial not because it's inconsistent, but because it sits beyond direct observation. We may never see another bubble, but their existence could explain why our universe seems so finely tuned for stars, planets, and life. Among countless bubbles, only a few will have the right conditions to ask why. When we look around, the universe seems simple. 3 directions in which we can move and one arrow of time that carries us forward, but physics has long hinted that this is only a thin slice of a much richer reality. Extra-spatial dimensions may exist folded so tightly or hidden so cleverly that we never notice them in everyday life. This idea isn't a fantasy. It naturally emerges from some of the deepest theories in modern physics, including string theory. In these frameworks, the fundamental particles of nature are not zero-dimensional points, but tiny vibrating strings. And those strings can only exist consistently if space has more than 3 dimensions. To visualize this, imagine an insect walking along a straw. From far away, the straw looks like a one-dimensional line, but the insect also has the option to crawl around its circular surface a hidden direction that an outside observer can't see. Similarly, we may live in a 3-dimensional surface while extra dimensions curl up on scales far too small for us to explore. These compactified dimensions could influence physics in subtle ways, shaping the masses of particles, the strength of forces, and even the behavior of gravity. If they exist, they might help explain why gravity is so weak compared to other interactions, because some of its strength leaks into those hidden directions. We've never detected these extra dimensions directly, but experiments are trying. High-energy collisions at particle accelerators like CERN search for missing energy that could signal gravity escaping into the bulk. Precision measurements of gravity at small scales also test for tiny deviations that extra dimensions might create. If proven, this would reshape our understanding of space. The universe would no longer be a 3-dimensional stage. It would be a vast structure with hidden hallways invisible to us, yet fundamental to how reality works. If extra dimensions truly exist, then our universe might not be the whole of reality. It could be just one surface, a 3-dimensional membrane floating in a higher dimensional space. This is the heart of brain cosmology, an idea born from string theory and developed into a full framework for how the cosmos might be structured. In this picture, all the familiar particles and forces, light atoms, stars and galaxies are trapped on our brain. They can move freely within its 3 spatial dimensions, but they cannot escape into the extra dimension surrounding it. Gravity, however, is different. Because it's a property of space-time itself, it can leak into the higher dimensional bulk. This could explain why gravity is so much weaker than other forces. Most of it isn't confined to our universe at all. Our brain could be drifting like a cosmic raft through a higher dimensional sea. Other brains might exist too, parallel universes separated not by distance within our space, but by layers in these hidden dimensions. They could be close in a way we can't visualize, perhaps just micrometers apart, yet forever unreachable, because our forces can't cross the gap. Some models even suggest that collisions between brains could ignite entire universes, providing alternative explanations for the Big Bang. In this view, the beginning of everything wasn't a single point of creation, but the spark from a higher dimensional encounter. Though speculative brain cosmology is mathematically elegant and deeply connected to the geometry of space-time, it doesn't just add more space, it adds layers of structure, hinting that the universe we see may be only a thin film on a much grander canvas. When we imagine the universe, we often picture it as a gigantic sphere floating in empty space. But that's a trick of human intuition. The cosmos doesn't need to sit inside anything to have a shape. Its geometry is woven into its very fabric. Understanding that shape its topology is one of the great quests of modern cosmology. In Einstein's theory, matter and energy curve space-time. That curvature determines whether the universe is open, flat, or closed. A closed universe is like the surface of a sphere. If you travel far enough in one direction, you might eventually return to where you started without ever encountering an edge. A flat universe stretches out endlessly like an infinite sheet, and an open universe curves like a saddle with space expanding forever. Crucially, none of these shapes require an outside, just as the two-dimensional surface of the Earth is curved without needing a third dimension to contain it. A three-dimensional universe can be curved within itself. It doesn't expand into anything, it expands within itself. Astronomers have spent decades searching for clues to this shape. Measurements of the cosmic microwave background by W.M. App and Planck show that the universe is astonishingly flat on large scales. But that doesn't rule out more exotic topologies. A flat space can still loop back on itself like a three-dimensional donut, finite yet without boundaries. If that's true, light could circle the cosmos and return from the opposite direction, creating repeating patterns in the CMB. So far no such signature has been found, but the search continues. The shape of the universe isn't a decorative detail, it's a fundamental part of its identity. And remarkably, it can exist without an external container. The cosmos shapes itself from the inside out. When cosmologists talk about the shape of the universe, they don't just mean whether it's flat or curved. They also mean how space is connected to itself. Two universes can have the same curvature but radically different topology. This is where things get wonderfully strange. A familiar example is the 3 torus, a three-dimensional version of a donut shape. In such a universe, if you travel in one direction long enough, you don't hit a wall. You loop around and return from the opposite side, just like a character in a video game that wraps around the screen. It's finite in volume, but has no edges at all. There are even more exotic possibilities. Spaces with multiple connections, twists, or handles. They can be compact in some directions, but infinite in others. To inhabitants like us, these topologies are invisible on small scales. Only by studying the cosmos as a whole, especially the cosmic microwave background, can we hope to detect their imprint. If the universe is multi-connected, light from a single cosmic object could take multiple paths to reach us, appearing in different places on the sky. Astronomers have searched for repeating patterns in the CMB, like matching circles on opposite sides of the sky. So far, no conclusive pattern has emerged, but the data is not precise enough to rule it out entirely. The deeper meaning here is profound. The universe can be finite without having a boundary. There's no outside waiting beyond some wall. Space can curve back on itself in ways our everyday intuition struggles to imagine. If one day we confirm such a topology, it would mean we are living inside a cosmic loop, a self-contained, boundary-less world, elegant and strange beyond words. We often think of time as a universal rhythm ticking evenly throughout the cosmos. But in reality, time is anything but absolute. It bends, it stretches, and it flows differently depending on where and when you are. This isn't just an effect of black holes or high speeds. It's built into the structure of an expanding universe. In general, relativity time is inseparable from space together. They form space-time. When space stretches, the intervals between events stretch too. That means the deeper into the past we look, the slower clocks appear to tick. Distant galaxies don't just look far away in space. They exist in a time when the universe itself ran at a different pace. This phenomenon is known as cosmological time dilation. A supernova that explodes in a galaxy billions of light years away doesn't just look dimmer. Its light curve unfolds more slowly. If the light is redshifted by a factor of 2, the explosion seems to last twice as long. To the supernova itself, nothing has changed, but to us its clock runs in slow motion. This isn't a trick of perception, it's a fundamental feature of the expanding fabric of space-time. The same redshift that stretches wavelengths also stretches time intervals. The farther we look, the more stretched the clock becomes, until at the cosmic horizon it effectively freezes. Our local experience of time-steady familiar linear is just one small patch in a vast, uneven temporal landscape. Out there across unimaginable distances, the universe's heartbeat slows to a whisper. When astronomers talk about redshift, they usually describe it as the stretching of light, a wave whose crests are pulled farther apart as the universe expands. But redshift isn't just about colour, it is also about time itself being stretched. The two are inseparable. Light is like a clock. Each wave crest is a tick. When space expands, it doesn't just stretch the distance between galaxies, it stretches the fabric through which those ticks travel. By the time the light reaches us, the interval between these ticks has grown longer. A wave that started out as ultraviolet may arrive as red, and an event that lasted 1 second where it happened may appear to last many seconds to us. This is why a supernova in a distant galaxy seems to unfold in slow motion. If its light has a redshift factor of, for example, 3, then the rise and fall of that explosion takes 3 times longer when observed from Earth. The same effect appears in the flicker of quasars in gamma-ray burst afterglows, and even in the faint whisper of the cosmic background radiation. In simple terms, the redshift factor read as 1 plus c stretches the length of any event we observe. The universe acts like a cosmic time machine, not by changing the past, but by slowing it down as light travels across expanding space. So when we look deep into the cosmos and see distant objects playing out their stories more slowly, we're not just witnessing a difference in distance. We're hearing the heartbeat of the universe itself stretched and softened across billions of years. Redshift and time dilation are not two separate phenomena. They are one and the same story told in the languages of light and time. As the universe expands faster and faster, something extraordinary happens. Time itself seems to slow down in distant regions of the cosmos. From our vantage point, galaxies far beyond are not only racing away but also aging more slowly. Eventually their clocks appear to freeze altogether. This effect isn't caused by some mysterious force acting on time. It's a direct consequence of accelerated expansion. As light travels from a distant galaxy to us, the space in between stretches more and more. Each tick of that galaxy's clock takes longer to reach us. The redshift grows without bound, and so does the time dilation. Events that happen there unfold at an ever slower pace from our perspective. There is a critical distance beyond which this effect becomes extreme. Galaxies crossing this line drift into what's called the cosmological event horizon. Their light is stretched so much that it never reaches us again. It's as if they've slipped over the edge of time. They continue to exist, but from our point of view, their clocks have nearly stopped. This isn't just theoretical. Observations already show that many galaxies are receding so quickly that their signals are dimming and slowing down dramatically. In the far future, most of the universe will fade beyond this horizon, leaving only our local group of galaxies visible. It's a haunting idea. Distant stars will not burn out suddenly. They will fade into a slow-motion silence frozen by the expansion of space itself. Time from our perspective will have nearly stopped for them, even as it flows normally here. The universe doesn't just separate us by distance, it separates us by time itself. When we look deep into space, we're also looking deep into the past. But there's more than one way to measure that past. Cosmologists use two different but equally important concepts: look-back time and proper time. Understanding the difference between them reveals why time in an expanding universe is more complex than it seems. Look-back time is the time that has passed for us since the light left a distant object. If a galaxy is 10 billion light-years away, we are seeing it as it was 10 billion years ago. This measure is anchored to our own clock, to the history unfolding here on Earth. Proper time, on the other hand, is the time experienced by the object itself. While the light was on its way to us, the universe continued to expand and that galaxy continued to age on its own timeline. But because the expansion of space dilates the signal, the image we receive is of a younger galaxy, a frozen moment in its past. Its proper time and our look-back time don't match. This mismatch grows with distance. The farther away something is, the larger the gap between its own clock and what we see. For the most distant galaxies, we may be looking at them as they were less than 1 billion years after the Big Bang, even though far more time has passed for us since then. This is why the universe doesn't have a single universal now. What we see is a layered history with every object frozen at a different point in time. Look-back time is our window into their past. Proper time is the story they've actually lived. When we gaze at the stars, we're not seeing the universe as it is. We're seeing the universe as it was, each piece caught in a different chapter of cosmic time. We often talk about space and time as if they were two different things, like a stage and a clock ticking above it. But the universe doesn't work that way. Space and time are woven together into a single structure, spacetime. Every stretch of space is also a stretch of time. Every tick of a clock is part of the geometry of the cosmos itself. This inseparability is why the expansion of the universe can never be understood as just galaxies moving away. What's actually expanding is the fabric of space-time. As distances grow, so do the intervals between moments. Redshift and time dilation are simply two faces of this same stretching. One written in light, the other in time. Think of space-time as a vast flexible sheet. When it stretches, both the grid lines of distance and the ticks of the cosmic clock stretch with it. There's no external metronome keeping universal time. Each observer, each galaxy carries its own clock, and those clocks diverge as the universe grows. This is also why asking what the universe looks like right now is meaningless on cosmic scales. There is no single universal now. Each distant object exists in its own slice of time, and what we observe is a layered history unfolding all at once. Understanding this unity between space and time transforms the way we see cosmic expansion. It's not movement through a container. It's the changing shape of the container itself, and time is built into that shape. The universe doesn't just stretch space. It stretches history. And we floating in this fabric are carried along with it. The night sky today is full of light. Stars burn in every galaxy, pouring energy into the darkness. But this brilliant era is temporary. In the distant future, when the last stars exhaust their fuel, the universe will enter a new age. Cold, silent chapter, sometimes called the era of darkness. Stars are engines with finite lifespans. Over trillions of years, even the smallest, slowest burning red dwarfs will eventually fade. One by one, galaxies will go dark, leaving only the faint glow of dying embers. By then, the universe will be far larger than it is now. Expansion will have pushed distant galaxies so far apart that their light can no longer reach each other. In this era, the only sources of light will be occasional collisions between stellar remnants. White dwarfs merging into brief flashes of brilliance, or neutron stars spiraling together in violent bursts of energy. But these events will be rare and grow rarer with time. The cosmos will settle into a vast and mostly featureless darkness. The great cosmic structures that define our universe today spirals clusters. Filaments will remain, but they'll be shadows of what they once were. Without stars, galaxies will be made of cold stellar corpses, white dwarfs, neutron stars, and black holes drifting in silence. To any observer existing in that age, the universe would look unimaginably empty. There would be no glowing band of the Milky Way in the sky, no nearby galaxies, no evidence of the vibrant star-filled cosmos we know. This is the beginning of the universe's slow fade, not a sudden end, but a quiet unravelling. A night without dawn. When the last stars go dark, the universe will not be empty. What remains will be the most enduring objects in existence. Black holes. They will dominate the cosmos long after the galaxies have faded, ushering in what physicists call the black hole era. These objects are not eternal stars or glowing suns. They are the collapsed remnants of massive stars and the supermassive monsters at the centres of galaxies. As the universe grows older, black holes will become the primary engines of change. They will slowly swallow whatever matter remains wandering planets, white dwarfs, neutron stars, and even other black holes. Over unimaginable spans of time, galaxies themselves may be consumed from the inside. In the distant future, gravitational interactions will fling most stellar remnants into intergalactic space, while the heaviest black holes sink toward the centre, merging into giants billions of times more massive than the Sun. But even these titans cannot last forever. According to Hawking radiation, black holes emit tiny amounts of energy, causing them to evaporate over time. For stellar mass black holes, this takes far longer than the current age of the universe. For supermassive black holes, it takes incomprehensible stretches of time, a number so large it dwarfs everything we can imagine. During this era, the universe will be dark, cold, and nearly static. The slow glow of Hawking radiation from black holes will be among the last sources of energy in the cosmos. The grand drama of stars and galaxies will be long over replaced by an almost silent dance of gravitational shadows. This will be the universe's long twilight, an age ruled by darkness itself. Black holes are often imagined as eternal prisons, swallowing everything and letting nothing escape. But even they have an expiration date. Thanks to Hawking radiation, these giants slowly lose mass, leaking away their energy bit by bit until they vanish completely. This radiation is not like the fierce light of a star. It's faint, born from quantum effects near the event horizon. In simple terms, the fabric of spacetime itself generates pairs of virtual particles. One falls in, the other escapes, stealing a tiny amount of energy from the black hole. Over an almost unimaginable span of time, this process drains the black hole away. For a black hole with the mass of a star, this evaporation takes about 10 to the power of 67 years, many orders of magnitude longer than the universe's current age. For a supermassive black hole, it takes closer to 10 to the power of 100 years. This is a timescale so vast that even entire galaxies are fleeting by comparison. As black holes shrink, their radiation grows hotter. In their final moments, they blaze with incredible intensity, releasing bursts of energy before fading into nothingness. When the last one dies, the universe will have lost its final concentrated sources of energy. What remains after this slow fade is not silence in the ordinary sense, but an almost perfect stillness. No stars, no galaxies, no black holes. Only a thin sea of low-energy particles stretched across an ever-growing void. The age of structure will have ended, and the universe will drift into the final stage of its story, a vast, quiet eternity. After the last black hole evaporates, the universe will enter its final act, a state known as heat death. This is not a violent ending, but a slow, inevitable fading into stillness. It's the point where the cosmos has reached maximum entropy, when energy is so evenly spread out that nothing more can happen. Today stars shine because there are differences in energy. Hot, dense regions radiate into cold, empty space. These gradients drive everything: the birth of stars, the glow of galaxies, the formation of life. But in the far future, those differences will disappear. Every last pocket of usable energy will have been spent, leaving a smooth bath of particles at an almost uniform temperature. In this frozen era, there will be no stars, no black holes, no planets. The cosmos will be a thin fog of photons, neutrinos, and whatever stable particles survive. Distances between them will continue to grow as space expands until even a single interaction between particles becomes almost impossible. Time will still flow, but nothing will change. From a thermodynamic perspective, this is the most natural end the universe can have. When there are no more energy gradients, no more structures to collapse, no more stars to burn. The arrow of time loses its meaning. Without change, time is just a silent dimension stretching forward into eternity. It's a haunting vision. Not a bang, not a collapse, but a whisper that fades until there's nothing left to hear. The universe will not end with an explosion. It will end with a quiet, infinite sigh. The quiet fade of heat death is not the only way the universe could end. There is a far more violent possibility, a cosmic catastrophe known as the Big Rip. In this scenario, the mysterious force driving cosmic expansion doesn't stay constant. It grows stronger with time, and one day it overwhelms every force that holds the universe together. Right now, dark energy pushes galaxies apart, but gravity still holds individual galaxies together. Stars remain bound to their clusters, planets to their stars' atoms, to their nuclei. But if dark energy's strength keeps increasing, this balance will collapse. Expansion will no longer just separate galaxies, it will tear apart everything. First, galaxy clusters will be ripped away from each other. Then individual galaxies will begin to unravel as stars drift off into the void. As the expansion accelerates further, entire solar systems will be torn apart. Planets will lose their orbits and stars will drift alone. Moments before the end, the acceleration will become so extreme that it overpowers even the forces inside atoms. The fabric of space will stretch faster than light can travel. Protons and neutrons will be ripped from each other. In the final instant, the structure of space-time itself will shatter. The timeline depends on the true nature of dark energy. If it grows stronger over time, the Big Rip might occur tens of billions of years from now, or it may never happen at all. We simply don't know yet. Unlike heat death, the Big Rip is not a fading of the universe. It is a violent self-destruction. A universe not drifting into silence but being torn apart by the very force that made it grow. No one knows how the universe will end, but based on everything we've observed, from the stretching of light to the behavior of dark energy, cosmologists have outlined a handful of possible destinies. Each one tells us something profound about the nature of space and time. The first scenario is heat death, a slow fade into a uniform sea of cold, thin radiation. No structures remain, no energy, gradients drive change, and time loses its meaning. It's the quietest ending and at present the most likely. The second is the Big Rip, a far more violent possibility. If dark energy grows stronger over time, expansion will accelerate without limit. Galaxies will be torn apart, then stars, planets, molecules, and finally space-time itself. The cosmos won't fade away. It will rip itself to pieces. Another scenario less favoured but still discussed is the Big Crunch. If dark energy were to reverse or gravity eventually won out, the expansion could slow stop and then collapse. Galaxies would fall back together. The universe would heat up and everything would end in a fiery, crushing finale, a mirror image of the beginning. Each of these endings is written in the same equations that describe the expansion we observe today. Which one happens depends on the true nature of dark energy, something we still know almost nothing about. The most remarkable part is this. The universe's fate isn't determined by something external. It's woven into the fabric of space-time itself. The same expansion that gave birth to galaxies will one day shape their end. Whether it fades, collapses, or tears itself apart, the universe carries the seed of its own destiny. The discovery of dark energy didn't just surprise physicists, it shook the foundations of theoretical physics. Not because the universe is accelerating, but because the numbers don't make sense. When scientists calculate the vacuum energy of space using quantum field theory, the predicted value is enormously larger than what astronomers actually observe. How large? The difference is about 10 a number so vast it defies intuition. If the quantum vacuum really carried that much energy, the universe would have ripped itself apart the instant it began. And yet here we are. This discrepancy is often called the cosmological constant problem. In theory, every quantum field contributes to the energy of empty space. Virtual particles flicker in and out of existence, adding up tiny amounts of energy everywhere. When physicists sum these contributions, they get a vacuum energy density far beyond anything compatible with the gentle acceleration we see through supernovae and the cosmic microwave background. So something is wrong or missing in our understanding. Either some unknown mechanism cancels out nearly all of this vacuum energy, or our theories of quantum fields and gravity don't fit together the way we think they do. This problem isn't just a mathematical annoyance. It sits at the very crossroads of cosmology and particle physics. Solving it might require a new framework that unites quantum mechanics with gravity, something physicists have sought for nearly a century. The quiet acceleration of the universe invisible to our eyes points to a mystery deeper than anything we've solved before. No one truly knows what dark energy is. The simplest explanation is that it's just a constant property of space. The same idea Albert Einstein once called the cosmological constant. But as with many things in cosmology, simplicity might not tell the whole story. Over the years, physicists have developed several competing models to explain the mysterious force pushing the universe apart. The first and most conservative model is indeed the cosmological constant, an unchanging vacuum energy that permeates all of space. It fits the data remarkably well and elegantly explains why expansion accelerates. But it leaves one huge question unanswered. Why is the value so small compared to quantum predictions? Another idea is quintessence, a slowly evolving energy field that changes over time. Unlike a constant vacuum, energy quintessence would have its own dynamics rising or falling as the universe expands. If correct, it could mean that cosmic acceleration is temporary, not eternal. A third and more extreme possibility is phantom energy, in which the repulsive force grows stronger over time. This would lead directly to the Big Rip scenario where galaxies, stars, and even atoms are torn apart. There are other more exotic models too, modifications to general relativity, extra-dimensional effects, or entirely new interactions we have yet to discover. Each model makes slightly different predictions about how expansion changes over time. Observations over the coming decades, from precise redshift surveys to next-generation space telescopes, may help distinguish between these possibilities. But for now, dark energy remains a blank space on the cosmic map. It is not just a number in an equation. It's a window into the deepest structure of reality. If dark energy is the force driving the universe's accelerated expansion, then understanding it is one of the most important scientific goals of our time. But dark energy doesn't shine, doesn't interact with matter, and doesn't leave fingerprints we can touch directly. To find it, astronomers must turn the entire cosmos into a laboratory. The main clue lies in how the expansion rate changes over time. If dark energy is a true cosmological constant, that rate should follow a smooth, predictable curve. But if it evolves as in quintessence or phantom models, subtle deviations will appear. Detecting those tiny shifts is the mission of some of the most ambitious surveys ever designed. Projects like the Dark Energy Survey Euclid mission and the Vera C. Rubin Observatory are mapping millions of galaxies across cosmic time. By measuring redshift brightness and the large-scale clustering of galaxies, they can reconstruct how fast the universe expanded at different epochs. Other observations focus on baryon acoustic oscillations, subtle ripples in the cosmic web that act like standard rulers, and on weak gravitational lensing where light is bent by mass distributions along its path. Both offer powerful independent ways to measure the geometry of space-time. The goal is simple but profound: to determine whether dark energy is truly constant or slowly changing. Even the smallest deviation would have enormous consequences for our understanding of physics. In the silence of the night sky, the universe is telling us its story through the motion of galaxies. By reading that story with enough precision, we may finally uncover the nature of the invisible force shaping its fate. When astronomers discovered that the universe is expanding faster and faster, the simplest explanation was dark energy. But what if the acceleration isn't caused by some mysterious new energy at all? What if it's a sign that our understanding of gravity itself is incomplete? Einstein's general relativity has passed every test within the solar system and on galactic scales, but it was never directly tested on the scale of the entire cosmos. Perhaps on these immense distances gravity behaves differently than we expect. Several alternative theories explore this possibility. Some modify Einstein's equations slightly, introducing extra terms that mimic the effect of dark energy. Others propose extra dimensions where gravity can leak away, weakening its pull on large scales and making expansion appear to accelerate. There are also bolder ideas. Perhaps space-time itself has an evolving structure that changes how it curves over time. In such models, the universe doesn't need an invisible energy to push it apart. It expands faster, simply because the geometry of gravity allows it. The challenge is that these modified gravity models must reproduce everything we already observe. The redshift of supernovae, the patterns of baryon acoustic oscillations, the temperature map of the cosmic microwave background and the way galaxies cluster. So far, general relativity has held up impressively well, but cosmologists are cautious. They know that dark energy might be less of a substance and more of a signpost, a hint that the fundamental laws we rely on are not the full story. If that's true, the ultimate solution may not lie in finding a new energy field, but in rewriting the rules of space and time themselves. The mystery of dark energy sits at the center of modern cosmology. It shapes the fate of the universe, yet we still don't know what it is, or even whether it truly exists as a form of energy. Solving this puzzle will require more than bigger telescopes. It will require a new way of seeing the cosmos. In the coming decades, next-generation observatories will map the universe with unprecedented precision. The Euclid mission in Europe, the Nancy Grace Roman Space Telescope in the United States, and the Vera C. Rubin Observatory in Chile will chart billions of galaxies, tracing how expansion has evolved over time. They'll combine multiple methods: redshift measurements, weak lensing, and large-scale structure mapping to narrow down how dark energy behaves. Meanwhile, particle physicists are probing the quantum vacuum from the opposite direction. If dark energy is tied to vacuum fluctuations, experiments in high-energy physics could offer clues about why its strength is so small. Colliders, precision detectors, and quantum gravity research may reveal mechanisms that cancel out most of that vacuum energy, leaving only the tiny remainder we observe. Some theorists believe the answer might come not from observation alone, but from a new synthesis of ideas, a framework that finally unites quantum mechanics with general relativity. If such a theory emerges, dark energy may turn out to be not a substance at all, but a natural property of space-time. Whether the future reveals quintessence, phantom fields, modified gravity, or something entirely unexpected, one thing is certain. Solving the dark energy puzzle will transform our understanding of the cosmos. It may even rewrite the story of how the universe began and how it will end. The story of Hubble's law is the story of how humanity first learned that the universe is not static, but alive, growing, stretching, and evolving with time. Before the 1920s, most scientists believed that the cosmos was eternal and unchanging. The stars seemed fixed, the galaxies close, and the universe, if they thought of it at all, was simply a quiet backdrop. That view began to unravel when Edwin Hubble pointed his telescope at faint, spiral-shaped nebulae and found something astonishing. These objects were far outside the Milky Way, and their light was stretched toward the red end of the spectrum. The more distant the galaxy, the stronger this redshift appeared. Hubble carefully measured the distances to dozens of galaxies and plotted them against their redshifts. What emerged was not noise, but a clear line. The farther away a galaxy is, the faster it seems to be receding. This simple, elegant relationship became Hubble's law, a cornerstone of modern cosmology. The implication was profound. The universe isn't static at all. Space itself is expanding, carrying galaxies with it like raisins embedded in rising dough. And crucially, no galaxy sits at the center of this motion. Every point sees the same expansion around it. Today, Hubble's law is confirmed with extraordinary precision through observations of thousands of galaxies. It remains one of the most powerful pieces of evidence that the universe began in a hot, dense state and has been growing ever since. It was not just a discovery of movement, it was discovery of time, the realization that the cosmos has a history and a future. The beauty of Hubble's law lies not only in its simplicity, but also in what it allows us to calculate. If galaxies are moving away from each other at a rate proportional to their distance, then by reversing that motion in time, we can estimate when everything was once much closer together. That moment when the universe was compact, dense, and hot is what we call the beginning of cosmic expansion. The key number here is the Hubble constant, a measure of how fast the universe is expanding today. Once astronomers know this value, they can estimate the age of the universe by asking a simple question. If everything has been moving apart at this rate, how long did it take to reach the present size? Early estimates gave wildly different answers, sometimes younger than the oldest stars, which was clearly wrong. But over the decades, observations became more precise. Using space telescopes to measure distances to faraway galaxies, and later using Type Ia supernova as cosmic distance markers, astronomers refined the Hubble constant. Today, measurements suggest the universe is roughly 13.8 billion years old. But attention remains. Local measurements of the Hubble constant disagree with values derived from the cosmic microwave background by a few percent. This discrepancy, known as the Hubble tension, may be a sign that something deep is missing from our understanding of cosmic expansion. Whether this gap is due to new physics measurement errors or some unknown effect, the age of the universe is no longer guesswork. It's calculated from the rhythm of cosmic expansion itself, a clock written into the fabric of space-time. When astronomers measure distances across the universe, they can't stretch a measuring tape or bounce signals off distant stars. Instead, they rely on special cosmic events that act like beacons in the dark. Among them, Type Ia supernova stands as one of the most powerful tools ever discovered. A Type Ia supernova occurs when a white dwarf star steals material from a companion star. When it reaches a critical mass, a runaway nuclear reaction ignites, destroying the star in a brilliant flash. Because this critical mass is nearly identical in every case, these explosions have almost the same intrinsic brightness no matter where they occur. By comparing their true brightness to how dim they appear from Earth, astronomers can calculate their distance with remarkable precision. At the same time, the spectrum of their light reveals the redshift, how fast the galaxy hosting the supernova is moving away from us. Combined, these two pieces of information allow us to measure how fast the universe has expanded over cosmic history. In the late 1990s, two independent teams used these cosmic lighthouses to make a shocking discovery. The expansion of the universe is not slowing down, it's speeding up. This was the first direct evidence for dark energy, a mysterious force woven into the fabric of space itself. From a handful of dying stars, humanity learned something extraordinary about the fate of everything yet to be born. These distant explosions are not just lights in the sky. They are milestones in the story of the universe. Long before galaxies formed, before stars ignited, before atoms even settled into stable structures, the universe was a hot and brilliant fog of plasma. That ancient fireball has not vanished. Its glow still fills the cosmos today as the cosmic microwave background, the oldest light we can observe, a silent messenger from the beginning. This light was released about 380,000 years after the Big Bang, when the universe cooled enough for protons and electrons to combine into neutral hydrogen. For the first time, light could travel freely through space without being scattered. That moment left behind a perfect snapshot of the early cosmos preserved in the fabric of the microwave background. When satellites like WMAP and Planck mapped this faint glow, they found it astonishingly uniform with tiny fluctuations in temperature, just a few parts in 100,000. Those minute ripples are the imprints of primordial density variations, the seeds from which galaxies' clusters and cosmic filaments would grow. The CMB does more than confirm that the universe had a hot, dense beginning. Its precise patterns reveal its shape, age, and contents. They show a universe that is nearly flat 13.8 billion years old and dominated by dark energy and dark matter. When we observe the microwave background, we're not just looking at the distant past. We are seeing the universe at its childhood, its earliest visible moment. Every tiny fluctuation in that light tells a piece of the story of how everything we see today came to be. In the early 20th century, physics stood at the edge of a revolution. Albert Einstein had just introduced general relativity, a breathtaking new vision of gravity not as a force, but as the curvature of spacetime itself. And almost immediately that vision confronted a problem. According to his equations, the universe could not sit still. It had to expand or collapse. This was deeply unsettling to Einstein. Like most scientists of his era, he believed the universe was eternal and unchanging. So he made a bold modification to his equations. He added a term called the cosmological constant. Its purpose was to introduce a repulsive force that would exactly balance gravity, holding the universe static in perfect equilibrium. For a moment it seemed elegant, but the equilibrium was fragile, like a pencil standing on its tip. Any tiny disturbance would cause the universe to either expand or collapse. Still, the idea of a static universe fit the philosophical beliefs of the time. It was calm, eternal, and reassuring. Then came a surprise. Observations by Edwin Hubble and others would soon reveal something no one expected. Distant galaxies are not sitting still. Their light is redshifted, meaning space itself is stretching. The universe is expanding. Einstein later called the cosmological constant his biggest blunder. But history has a sense of irony. The very term he introduced to keep the universe static would return decades later. Not as a mistake, but as a key to understanding dark energy and the accelerating cosmos. In the 1920s, the idea of a static eternal universe still ruled science, but Edwin Hubble, working at the Mount Wilson Observatory, was about to overturn that view forever. With a powerful telescope aimed at what were then called spiral nebulae, he began to measure their distances and analyze their light. What he found would shake the foundations of cosmology. Hubble's first breakthrough came when he identified Cepheid variable star in one of these nebulae. These stars brighten and dim at regular intervals, and their period is tightly linked to their true luminosity. That meant Hubble could calculate how far away these galaxies really were. The results were shocking. They lay far outside the Milky Way. The universe was vastly larger than anyone had imagined. Then came the second discovery, redshift. The spectral lines of these distant galaxies were shifted toward the red end of the spectrum, and the farther away a galaxy was, the stronger its redshift appeared. Plotting these values together produced a straight line, the relationship now known as Hubble's law. This was undeniable evidence that the universe is expanding. The galaxies weren't moving through space like projectiles. Space itself was stretching, carrying them apart. Hubble's measurements forced physicists to abandon the static universe model. Albert Einstein, upon visiting Hubble's observatory, reportedly admitted that his cosmological constant had been unnecessary. What had once seemed a blunder was actually the hint of something far greater. The fall of the static universe was not just a scientific correction. It was the moment humanity realized that cosmic history has a beginning and perhaps an end. After Edwin Hubble revealed that the universe is expanding, the cosmological constant, once central to Albert Einstein's static universe, seemed to lose its purpose. If the cosmos was already expanding on its own, no extra repulsive force was needed to hold it in balance. For decades, cosmologists set the constant to zero and moved on. The leading model became the simple expanding universe described by Friedmann equations. In this vision, the universe would either expand forever or eventually slow down and collapse under its own gravity depending on its total matter content. Einstein himself reportedly called the cosmological constant, his biggest blunder believing it had been nothing more than a mathematical trick to fit his personal expectations. Textbooks largely abandoned it. The great debates of mid-century cosmology focused on other questions. Whether the universe had a beginning, the Big Bang, or had always existed in a steady state. But the constant never fully disappeared. A few theorists kept it alive in the background, noting that nothing in Einstein's equations required it to be zero. And as physicists developed quantum field theory, new puzzles emerged. Quantum vacuum fluctuations seem to imply that empty space might have its own energy, precisely the kind of effect a cosmological constant would represent. For most scientists, though, this was still just a mathematical curiosity disconnected from observations. The universe, as far as anyone could tell, was coasting along under the steady pull of gravity. Then, at the end of the 20th century, new measurements would shatter that calm. The cosmological constant was about to return not as a mistake, but as a revelation. In the late 1990s, cosmology experienced one of the most shocking discoveries in its history. Two independent teams of astronomers, the Supernova Cosmology Project and the High Z Supernova Search Team, set out to measure how fast the expansion of the universe was slowing down. Instead, they found something entirely unexpected. It was speeding up. Their strategy relied on Type-R supernova, those brilliant explosions with nearly identical luminosities. By comparing their apparent brightness with their redshift, the teams could reconstruct the expansion history of the cosmos. If gravity-dominated distant supernovae should appear slightly brighter than expected, a sign of deceleration, but they were dimmer. The only explanation that fit the data was acceleration. Something was pushing the universe apart faster and faster. That something behaved exactly like a cosmological constant, a uniform energy density filling space itself. The results stunned the scientific community. A term once considered Einstein's greatest blunder had returned not as a mistake, but as the key to understanding a deeper cosmic truth. In 2011, the leaders of the two teams received the Nobel Prize in Physics for this discovery. The re-emergence of the cosmological constant forced cosmologists to rethink their models. Matter alone could not explain the universe's expansion. Roughly 70% of the cosmos seemed to be made of something invisible, unchanging, and repulsive dark energy. It was a turning point. Cosmology had moved from mapping the universe's past to confronting its mysterious future. When dark energy burst onto the scene in 1998, it didn't just change one equation. It reshaped the entire framework of cosmology. The cosmological constant, once abandoned as an obsolete relic, became the simplest and most powerful way to explain the accelerating universe. What had started as Albert Einstein's mathematical trick to keep the universe static was reborn as the engine of cosmic expansion. In the new picture, space itself is filled with a constant energy density. Unlike matter, which thins out as the universe grows, this energy does not dilute. The more space expands, the more of it there is. This realization gave rise to what is now called the lambda CDM model. Lambda for the cosmological constant and CDM for cold dark matter. This model describes a universe that is about 5% normal, matter 25% dark matter and 70% dark energy. It's astonishingly simple, yet it fits nearly all cosmological observations with remarkable precision. Ironically, Einstein's blunder now sits at the core of our best theory of the cosmos. It explains the expansion history, the shape of the cosmic microwave background, the formation of large-scale structure, and even the ultimate fate of the universe. But this success comes with a cost. While the cosmological constant fits the data perfectly, we still have no idea why its value is so small or what it really represents. It is both a triumph and a profound mystery. Dark energy turned an old idea into the foundation of modern cosmology, but it also reminded scientists how much of the universe remains hidden from our understanding. The discovery of dark energy marked the beginning of a new chapter in our understanding of the universe. For most of the 20th century, cosmology was about mapping what we could see: galaxy stars, gas and radiation. But now scientists must grapple with what they cannot see, the invisible force shaping cosmic destiny. The rebirth of the cosmological constant as a central pillar of the lambda CDM model gave cosmology a precise, elegant framework. It allowed researchers to predict the past and future of the cosmos with extraordinary accuracy. Observations of the cosmic microwave background galaxy clustering and baryon acoustic oscillations all fell beautifully into place. Yet the deeper scientists looked, the stranger the universe became. Roughly 70% of its content is dark energy, 25% is dark matter, and only 5% is ordinary matter, the stuff of stars, planets, and people. This means everything we have ever seen from distant galaxies to our own existence is just a tiny fraction of the whole. The great triumph of modern cosmology is that it can describe the evolution of the universe with a few simple parameters. Its great frustration is that we don't truly understand the nature of most of those parameters. What is dark energy? Why does it have the value it does? Is it truly constant, or does it evolve? The answers to these questions will define the next century of cosmology. We have mapped the outlines of the cosmic story, but the true plot remains hidden, waiting to be revealed. The universe may be far stranger than it seems. Even though cosmologists often describe it as infinite, this is not something we can ever observe directly. What we can measure is only the observable universe, the sphere of space from which light has had time to reach us since the Big Bang. Beyond that, reality could be far more complex. One of the most fascinating possibilities is that the universe is finite but unbounded. Imagine the surface of a sphere. It has no edge, but if you travel far enough in one direction, you return to your starting point. A three-dimensional analogue of this idea, a closed, multi-connected topology, could allow a finite universe to appear infinite to any observer inside it. In such a universe, light could wrap around space, creating repeating patterns in the cosmic microwave background. Galaxies might appear more than once in different directions, like reflections in a hall of mirrors. The cosmos could effectively tile itself, and we would never notice unless we detected these subtle repetitions. This idea is not science fiction. Cosmologists actively search for these signatures by looking for matched circles in the CMB precise alignments that might reveal the shape of space itself. So far, no clear signal has been found, but the possibility remains open. A finite universe without boundaries doesn't contradict cosmic expansion. It simply expands as a whole, just as the surface of a balloon grows without revealing an outside. In this way, the cosmos may not stretch into infinity. It may be folding in on itself, vast but finite, an elegant loop without edges. If the universe has a hidden shape, the faint glow of the cosmic microwave background may be the best place to find it. That light released just 380,000 years after the Big Bang carries an imprint of the geometry of space itself. Tiny fluctuations in temperature measured in millionths of a degree form a cosmic fingerprint that reveals how the universe is curved, connected, and structured. One of the key predictions of a multi-connected universe is pattern repetition. If space loops back on itself, light from a single patch of the early universe could travel along different paths and arrive from multiple directions. On the sky, this would show up as matching circles in the CMB, identical patterns of fluctuations appearing in different places like overlapping reflections in a mirrored room. Satellites such as WMAP and Planck have mapped the CMB with exquisite precision, allowing cosmologists to hunt for these signatures. So far, no clear repeating patterns have been found, but the data do place strong limits on the minimum size of any closed topology. If the universe is finite, it must be larger than the observable cosmos, big enough that the patterns lie beyond our cosmic horizon. Even the absence of repeating structures is a powerful clue. It tells us that space is either extremely large or truly infinite, and if future missions detect faint, subtle symmetries, we may finally glimpse the true shape of the universe itself, not as an abstraction, but as something written in the oldest light we can see. The sky is more than a view, it's a map, and buried in its patterns may be the blueprint of the cosmos. The greatest trick the cosmos may play on us is making a finite universe look infinite. No matter how advanced our telescopes become, we can only observe as far as light has had time to travel since the Big Bang. That distance, about 46 billion light-years in every direction, defines the edge of our observable universe. Anything beyond it is hidden not by distance alone, but by time. This means even if the universe loops back on itself, creating a closed and finite structure, it may simply be too large for us to notice. Light might not have had enough time to wrap around space and reach us again. To an observer trapped inside the world would appear endless, stretching outward in all directions without repetition. This illusion is powerful because our measurements are confined within a single cosmic horizon. Imagine standing on a vast fog-covered plain. You might believe the landscape goes on forever, but in truth you're just unable to see its edge. Cosmologists try to overcome this limitation by searching for subtle geometric clues, the curvature of space-matching patterns in the cosmic microwave background, or gravitational lensing signatures that reveal global topology. So far, all evidence points to a universe that is either extremely large or truly infinite, but there is a limit to what observation can reveal. If the scale of the cosmos is much larger than what light can traverse in the age of the universe, we may never know its true shape. Infinity, in other words, might be an illusion born of our perspective, a cosmic trick written into the fabric of space and time. No matter how powerful our telescopes become, we're confined to a single vantage point in space and time. The observable universe is like a glowing shell defined not by distance alone, but by the age of light itself. Beyond it, light hasn't had enough time to reach us. The cosmos may continue endlessly, but our knowledge stops at the cosmic horizon. This limitation isn't just practical, it's fundamental. We cannot build a telescope that sees faster than light, nor can we step outside our cosmic position to get a wider view. Our entire understanding of the universe is built from this one ever-expanding bubble of observation. Even the cosmic microwave background, the oldest light we can see, is not a wall of the universe. It's simply the surface beyond which the universe was opaque. Everything before that time is hidden from direct view. We can infer what happened from theory and indirect signals, but we can't observe it the way we observe galaxies and stars. This means our picture of the universe is always incomplete. We can map its structure, measure its curvature, estimate its age, and model its future, but we cannot know for sure whether it loops back on itself, whether it has edges, or whether it continues infinitely. This uncertainty isn't a flaw in science, it's part of the nature of reality. The horizon is not just a physical boundary, it's a boundary of knowledge. In a way, the most profound mysteries of the cosmos are not hiding behind distant galaxies. They're hiding just beyond what light has had time to reveal. When we imagine the universe, it's easy to picture it as a kind of giant bubble floating in a larger space. But this picture is misleading. The universe doesn't sit inside anything. It is space itself, the stage and the play at once. Asking what lies beyond its edge is like asking what's north of the North Pole. There is no outside in the conventional sense. This is the power of a universe without boundaries. In such a cosmos, the concept of an edge simply doesn't exist. Space can be finite in size, yet unbounded, curving back on itself like the surface of a sphere. It can also be infinite, stretching endlessly in every direction. In either case, there is no outer wall to hit, no final frontier to cross. Cosmological models based on general relativity describe spacetime as a self-contained structure. Expansion doesn't mean the universe is growing into empty space. It means the distances within it are increasing. Galaxies aren't flying through a void. The void itself is stretching. This perspective is difficult to visualize because our everyday intuition is built in a three-dimensional world with edges and outsides. But the universe doesn't have to obey our intuition. If the cosmos truly has no boundary, then there is no privileged vantage point, no center, and no edge. Everything is contained within the geometry itself. This is the quiet, astonishing truth behind cosmic expansion. The universe doesn't grow into anything, it simply grows. The grand structures of the universe, galaxies, clusters, filaments stretching across hundreds of millions of light years began as almost imperceptible ripples. In the early universe, shortly after the Big Bang, matter was distributed with near-perfect uniformity. Only tiny fluctuations, 1 part in 100,000, disturbed that smoothness. Yet those fluctuations became the skeleton of the cosmos. These primordial ripples are preserved in the cosmic microwave background as faint temperature variations. Regions slightly denser than their surroundings had a bit more gravity, so they pulled in more matter over time. These regions grew, forming knots in the invisible cosmic fabric, while the emptier regions became vast voids. As billions of years passed, these small seeds amplified through gravitational instability. Matter flowed toward the dense spots, collapsing into sheets and filaments, forming the backbone of what is now called the cosmic web. Galaxies condensed like dew along these filaments, while clusters formed where multiple strands intersected. This process is astonishingly efficient. From fluctuations measured in microkelvin in the CMB, the universe grew the complex large-scale structure we see today, and the same laws of physics apply everywhere. The patterns of clustering on the largest scales reflect those tiny ripples from the very beginning. The cosmic web is not just a collection of galaxies, it is a vast interconnected structure, a fossil record of the earliest whispers of creation. Once the tiny fluctuations of the early universe were in place, gravity took over as the great architect. Slightly over-dense regions pulled in more matter, growing heavier, which in turn attracted even more. This runaway process, called gravitational instability, slowly transformed faint ripples in the cosmic microwave background into the vast structures we observe today. But gravity did not work alone. At the same time, the cosmic expansion stretched space-pulling galaxies and matter apart. These two forces competed. Gravity trying to gather matter together, expansion trying to scatter it. Where matter was slightly denser than average gravity, one allowing structures to grow. Where it was less dense, expansion prevailed, creating the cosmic voids. Over billions of years, these contrasts sharpened. What began as gentle ripples became great filaments, clusters and superclusters, the scaffolding of the cosmic web. The largest structures we see today span hundreds of millions of light years, though most of the universe is still empty space. Interestingly, this growth isn't uniform. As dark energy accelerates the expansion, the formation of new large-scale structures slows. Galaxies that are not already gravitationally bound drift farther apart, and the cosmic web gradually freezes into place. In a sense, we live in a special era when the cosmic skeleton is still visible, but its growth has nearly stopped. Billions of years from now, much of this structure will fade beyond our cosmic horizon. The cosmic web is not a poetic metaphor, it's a literal structure, the largest known pattern in the universe. Galaxies, clusters, and dark matter are arranged in a vast, intricate network that resembles the filaments of a spider's web stretched across billions of light years. At its core, the web is built from 3 main components: filaments, walls, and voids. Filaments are the long, thin threads where galaxies and dark matter are most concentrated. Walls are the flattened regions between filaments like cosmic membranes. And voids, the vast, nearly empty bubbles in between, make up most of the universe's volume. These aren't random features. They emerge naturally from the way gravity amplifies small fluctuations in the early universe. Where multiple filaments intersect, enormous clusters form. These are the densest nodes of the web gravitational giants that can contain thousands of galaxies bound together. Along the filaments, galaxies flow inward like rivers converging toward a basin. Meanwhile, the voids continue to expand, pushing matter into the surrounding structures. Simulations have shown that this network isn't static. Over cosmic time, filaments grow thinner and longer. Clusters become more massive and voids widen. The web evolves under the combined influence of gravity expansion and dark energy. From our vantage point in the Milky Way, we sit on a quiet branch of one of these filaments, orbiting within a structure that connects us to superclusters far away. The cosmic web is the scaffolding of everything, the universe's hidden architecture, invisible yet shaping all that we see. The cosmic web we see today owes its shape to something we cannot see. Dark matter, invisible, elusive and dominant, acted as the silent architect of cosmic structure long before the first stars ever shone. In the early universe, ordinary matter was coupled to radiation, unable to clump together because light pressure kept it smooth and uniform. But dark matter, unaffected by electromagnetic forces, began collapsing into dense halos almost immediately after the Big Bang. These invisible clumps became gravitational well seeds into which ordinary matter would later fall once the universe cooled. Without dark matter, galaxies might never have formed. It concentrated mass on large scales, accelerating the growth of structure, while radiation still dominated the cosmos. As the universe expanded and cooled, ordinary matter finally decoupled from light, streaming into the preformed dark matter halos and igniting the first stars. Even today, dark matter remains the backbone of every galaxy. Observations of galaxy rotation, curves, gravitational lensing, and the clustering of galaxies all point to vast halos of unseen mass surrounding luminous structures. The cosmic microwave background itself bears the fingerprints of dark matter's early influence. Although it makes up about 25% of the universe, its true nature remains unknown. Is it made of undiscovered particles? Something more exotic? Whatever it is, dark matter sculpted the large-scale architecture of everything we see, a hidden hand shaping the visible universe. The cosmic web is mostly invisible. Its threads are made not of shining stars but of dark matter, which neither emits nor absorbs light. Yet astronomers have learned to map this hidden structure with extraordinary precision, using the luminous galaxies that trace its skeleton and the subtle distortions it leaves in the light. One of the most powerful tools is galaxy redshift surveys. By measuring the positions and redshifts of millions of galaxies, astronomers can reconstruct their three-dimensional distribution in space. Massive projects like the Sloan Digital Sky Survey and Dark Energy Spectroscopic Instrument have revealed vast filaments, walls and voids spanning hundreds of millions of light-years. But galaxies alone are only the tip of the iceberg. To map the dark matter beneath, scientists rely on weak gravitational lensing, the tiny bending of light from distant galaxies as it passes through massive structures. By measuring these subtle distortions statistically across millions of galaxies, cosmologists can build detailed maps of dark matter itself, independent of the light it doesn't produce. Another technique uses the Lyman alpha forest delicate absorption lines in the spectra of distant quasars that trace the diffuse gas between galaxies. These faint patterns reveal how matter is distributed along the cosmic filaments stretching through intergalactic space. Through these methods, astronomers have turned the invisible into something tangible, a cosmic network mapped with stunning clarity. What began as theoretical predictions is now a measured reality. The dark web of the universe has come into view not with eyes, but with the patient accumulation of light's whispers across billions of years. Long before astronomers could map the cosmic web through observation, they tried to build it inside computers. Cosmological simulations, vast intricate calculations run on some of the most powerful supercomputers on Earth, have become one of the most important tools for understanding how structure in the universe forms and evolves. These simulations begin with the faint fluctuations recorded in the cosmic microwave background. By feeding these initial conditions into equations governed by gravity, dark matter and cosmic expansion, scientists can let a virtual universe grow. Over billions of simulated years, those tiny ripples stretch, collapse and merge, weaving together the filaments and clusters we see in real surveys. The results are stunning. Simulations like Illustri's and Millennium Simulation produce cosmic webs that match observations in exquisite detail. Not only do they replicate the distribution of galaxies, but they also reveal the hidden structure of dark matter, the vast scaffolding on which the luminous cosmos hangs. By changing parameters, the amount of dark matter, the strength of dark energy, the laws of gravity, researchers can see how the cosmic web would evolve under different physical conditions. In this way, simulations become a cosmic laboratory, letting us test scenarios that no telescope could ever observe directly. When astronomers look at these virtual universes, they are not just running code. They are watching the story of structure unfold, a mirror of the real cosmos grown from the same primordial whispers. The cosmic web is a monument to the early universe, a structure billions of years in the making. But like everything else in the cosmos, it too has a future, and that future is one of slow dissolution. Today, gravity and dark energy are locked in a cosmic tug-of-war. Gravity pulls matter together, building clusters and filaments. Dark energy stretches space-pushing structures apart. For most of cosmic history, gravity dominated locally, allowing the web to grow and flourish. But as dark energy accelerates expansion, this balance is shifting. In the far future, galaxies not already bound to each other will be swept beyond our cosmic horizon. Filaments will thin, voids will grow, structures that once stretched across hundreds of millions of light years will dissolve into isolated islands of gravity. The cosmic web won't collapse, it will simply fade away, stretch so far that its connections vanish from view. Eventually, even the largest superclusters will be cut off from the rest of the universe. Only tightly bound structures like galaxy groups and clusters will remain intact. From the perspective of distant civilizations, the cosmos will seem increasingly empty, as if they are alone in a dark, silent ocean. The web we see today exists at a unique moment in cosmic history, when its filaments are still bright, its pattern still visible, and its reach still vast. Future observers trillions of years from now may never know it was there. The cosmic web is not eternal. It is a fleeting masterpiece written in the fabric of space before being stretched beyond recognition. When we look into the sky, it may seem like there's no limit to how far we can see, only more galaxies, more darkness, more space. But in reality, there are two invisible horizons that define the edges of our observable universe: the particle horizon and the event horizon. The particle horizon marks the maximum distance from which light has had time to reach us since the Big Bang. Even if the universe is larger or infinite, we simply can't observe beyond this limit because light from those regions hasn't had enough time to arrive. This is the boundary of what we can currently see. The event horizon, on the other hand, is more subtle. It defines the farthest distance from which light will ever be able to reach us in the future. Because cosmic expansion is accelerating, galaxies beyond this limit are receding faster than light can ever catch up. No matter how long we wait, their signals will never arrive. Together, these horizons create a kind of cosmic cage. We live inside a bubble of information defined by the age of the universe and the accelerating expansion of space. Everything outside remains forever beyond our grasp, not because it doesn't exist, but because causality itself forbids contact. Understanding these boundaries is crucial. They shape what we can learn, what we can measure, and what we can never know. The universe may be infinite, but our window into it is not. Every second more of the universe crosses an invisible boundary. Galaxies that were once observable are now receding faster than light can ever bring their signals back to us. This is the quiet work of cosmic expansion driven by dark energy stretching space itself faster than causality can keep up. This is why the event horizon is so profound. Galaxies beyond this limit are not merely far away, they are forever unreachable. No matter how long we wait, their light will never arrive. Even if humanity endures for trillions of years, those galaxies will remain locked outside the realm of the knowable. The particle horizon defines what we can see now. The event horizon defines what we can ever see. And with each passing moment, more galaxies slip from one side of that line to the other. Their light still travels toward us for a time, but eventually it redshifts into undetectable wavelengths and disappears into the darkness. This is not because space is finite or because they've vanished, but because the very geometry of space-time prevents their signals from ever reaching us again. In the unimaginably distant future, only a small handful of galaxies gravitationally bound to us will remain visible. The rest of the universe will fade into silence as if it never existed at all. This is one of the strangest consequences of living in an accelerating universe. The more time passes, the less of it we will ever be able to know. In everyday life, cause and effect seems simple. A stone hits water, ripples spread outward. A flash of light eventually reaches your eyes. But in an accelerating universe, this clarity breaks down on the larger scales. The event horizon places a hard boundary on what events can ever influence us or anything else. Causality depends on signals, and signals are limited by the speed of light. When space expands slowly, distant galaxies can still communicate with us eventually. But when space expands faster than light can cross those regions, become causally disconnected. No force, no signal, no spacecraft, nothing can bridge the growing gap. This means the universe is not a single perfectly connected arena. Instead, it is fracturing into isolated regions, each with its own causal domain. Over cosmic time, our local group of galaxies will become an island adrift in an ever larger ocean of unreachable space. This breakdown of causality isn't just philosophical, it shapes the limits of physics itself. Theories must respect these boundaries. Observations must work within them. And future civilizations, if they exist, will inherit an impoverished view of the cosmos, stripped of the distant galaxies that once illuminated the night. In a sense, cosmic acceleration writes a kind of event horizon around knowledge itself. Beyond that boundary, the universe still exists, but it might as well not because it can never speak to us. The structure of space-time doesn't just determine where galaxies are, it determines what can cause what and what can never touch us again. When we speak of the universe, what we really mean is the observable universe, the sphere of space from which light has had time to reach us since the Big Bang. But this is not the entire cosmos. It is only a single patch, a thin slice of something vastly larger, perhaps infinitely so. The particle horizon, event horizon, and the shape of our light cones together define this limited perspective. Everything beyond them may exist, but it can never communicate with us. From our vantage point, that distant reality is as unreachable as if it belonged to another universe entirely. This limitation is not a failure of our instruments. It is built into the very geometry of space-time. As the universe expands, more and more regions slip permanently beyond our horizon. What we can observe today is already more than what distant future observers will ever see. Their sky will grow emptier with time, their knowledge more constrained. Cosmologists suspect that the true universe could be unimaginably larger, perhaps composed of many regions like ours, each with its own horizons, each a silent island in an endless cosmic ocean. This realization changes how we think about everything. Our most precise cosmological models describe only one bubble of reality among countless others. The universe we see is not the universe as a whole. It is a local chapter in a story written across a far greater stage. We are quite literally living inside a fragment of the cosmos. The mystery of dark energy is not just a puzzle about cosmic expansion. It may be the missing link between the two greatest pillars of modern physics, quantum mechanics and general relativity. These two theories describe reality on vastly different scales, the subatomic and the cosmic, and they work with breathtaking precision. But they do not fit together. General relativity tells us how space-time bends and evolves. Quantum mechanics reveals a world of fluctuations, uncertainty, and fields. When we try to combine them, especially at extreme energies, their equations explode into contradictions. Yet dark energy sits precisely at this intersection. Quantum theory predicts a vacuum energy density far larger than what cosmological observations allow by a factor of about 10 to the power of 120. This is the so-called cosmological constant problem, one of the greatest unsolved mysteries in physics. It tells us something profound is missing in our understanding of how quantum fields interact with gravity. If we can explain why the vacuum energy has its observed value, or why it behaves the way it does, we may finally bridge the gap between the quantum world and the geometry of space-time. Dark energy could be the quiet whisper of a deeper, unified theory. In that sense, the accelerating universe isn't just telling us about its fate. It's giving us a clue to the deepest structure of reality, a doorway to the long-sought theory of quantum gravity. The accelerating expansion we observe today may be echoing a much older event. In the first fractions of a second after the Big Bang, the universe is believed to have undergone cosmic inflation, a period of unbelievably rapid expansion, far faster than anything occurring today. Though inflation ended long ago, its mechanism may be intimately connected to dark energy. Both phenomena involve a form of energy embedded in space itself, a repulsive pressure that drives expansion. During inflation, this energy dominated everything, blowing up quantum fluctuations into macroscopic ripples that became the seeds of structure. Today, dark energy dominates again, stretching space on a far gentler but still accelerating scale. Many physicists suspect this is not a coincidence. Perhaps both inflation and dark energy arise from similar underlying physics vacuum energy, or a slowly evolving field that once had a high energy state and now rests at a much lower one. If so, dark energy might be a faint remnant of the same process that launched the universe. Observations of the cosmic microwave background already show inflation's fingerprints in the form of tiny temperature fluctuations. Future experiments may detect even subtler signals linking the dawn of time with the universe's far future. In this view, cosmic acceleration is not two separate mysteries, but one long story. The universe began in a burst of expansion, and it may end in another. The quest to understand dark energy has blurred the boundaries between two great domains of science, cosmology and particle physics. Once these fields explored very different frontiers, one studying the largest structures in existence, the other probing the tiniest building blocks of matter. But as we push deeper into the nature of space-time, their paths are converging. The early universe was both a cosmic laboratory and a particle accelerator beyond anything we could ever build on Earth. In its first moments, temperatures and energies were so extreme that quantum fields shaped the expansion of space itself. Whatever mechanism drove cosmic inflation may have involved fields similar to those we explore in high-energy physics today. Dark energy, too, may have a particle physics origin. It could be a vacuum effect, the energy of a scalar field like quintessence, or the result of some unknown symmetry in nature. Clues may come from experiments on both ends of the scale, precise measurements of cosmic expansion, and powerful colliders searching for new particles or forces. Even subtle effects, tiny deviations in the cosmic microwave background, shifts in large-scale structure, or unexpected signals in detectors might reveal the physics behind dark energy. Cosmology has become a precision science, and its measurements now rival those of particle accelerators in their power to test fundamental physics. In the end, solving the dark energy puzzle may not belong to one field or the other. It may emerge from the union of both a single story linking the smallest quantum fluctuations to the largest cosmic structures. If dark energy holds the key to understanding the universe's fate, then the next few decades may bring the most decisive answers yet. Around the world, astronomers are preparing new observatories and space missions designed specifically to probe cosmic expansion with a level of precision never before possible. One of the most ambitious efforts is the Nancy Grace Roman Space Telescope, planned to map the shapes and distances of hundreds of millions of galaxies. By combining weak gravitational lensing and precise redshift measurements, Roman will chart how the universe's structure has evolved and how dark energy has shaped that evolution. Meanwhile, the Euclid mission launched by Europe is scanning a third of the sky to build a detailed three-dimensional map of the cosmos. Its goal is to measure the geometry of the universe and test whether dark energy behaves like a cosmological constant or something more exotic. On the ground, the Vera C. Rubin Observatory will create the deepest, most detailed time-lapse of the night sky ever made. Over 10 years, its legacy survey of space and time will track billions of galaxies, revealing subtle patterns in their motions and distributions. Together, these missions will do more than refine numbers. They will test entire theories. If dark energy evolves over time, these observatories will see it. If gravity behaves differently on cosmic scales, they will catch it. And if the cosmological constant truly is constant, they will confirm it with overwhelming precision. The universe is speaking through its expansion. Soon we'll have sharper ears to listen. For more than a century, general relativity has described the fabric of space-time with breathtaking precision. It predicted gravitational waves, black holes, and the bending of starlight, and every test so far has confirmed its power. But dark energy may push Einstein's theory to its breaking point. If cosmic acceleration is caused by something other than a true cosmological constant, then the behavior of gravity on the larger scales might not match Einstein's equations exactly. Even tiny deviations, a small difference in how galaxies cluster, or how light bends around massive structures, could signal a deeper theory beneath general relativity. That's why the upcoming generation of observatories, including Euclid, Nancy Grace Roman Space Telescope, and Vera C. Rubin Observatory, are so crucial. They are designed not only to measure cosmic expansion, but also to test gravity itself at scales far beyond anything achievable in the lab. By mapping weak-lensing galaxy clustering and the growth of structure, these missions will check whether gravity behaves exactly as Einstein predicted. Even a subtle mismatch could point toward new physics, perhaps extra dimensions, modified gravity, or interactions between space-time and quantum fields that we've never seen before. Dark energy, then, is not just a mystery to be explained. It is a pressure point on our best theory of the universe. If Einstein's equations bend even slightly, the next decade of cosmology may reveal where they finally break. As powerful as our science may become, the universe will always keep some of its secrets. The particle horizon and event horizon are not just boundaries of observation, they are boundaries of knowledge itself. Even with perfect instruments, there will always be regions forever hidden from us. Events we can never witness and truths we can never test. This limitation isn't technological. It's woven into the geometry of space-time. Light can only travel so far in a finite age, and space can expand faster than light can cross. No experiment, no future civilization can reach beyond those limits. The universe is not just vast. It is fundamentally unknowable in certain directions. But far from being discouraging, this gives cosmology its unique power. Within these boundaries, we've learned the age of the universe, mapped its structure, identified its hidden components, and traced its story back to its earliest moments. We've peered into the deep past, glimpsed the far future, and discovered that even the smallest fluctuations gave birth to everything we see. Science, in this sense, is not about knowing everything. It's about learning everything we can and understanding why some questions may never be answered. Standing at the edge of cosmic knowledge is not a failure. It's a privilege. The horizon doesn't diminish the wonder of the universe. It makes it infinite. If nothing exists outside the universe, what is it expanding into? This question has guided everything we've explored. The universe isn't growing into something. It's growing within itself. There is no external space, no invisible container waiting for it. Space-time itself is stretching, and every galaxy, every void, every photon is carried along with it. Our everyday intuition struggles with this. Balloons expand into airwaves, travel across water, but the universe is not a thing in space. It is space. What we call outside simply doesn't exist. The fabric of reality has no edge. This idea isn't poetic speculation. It's what emerges from general relativity Hubble's law and every cosmological observation we've made. The cosmic expansion doesn't push against anything. It simply is. This is the quiet, elegant truth hidden beneath the chaos of galaxies. The universe expands not into space, but as space itself. We live in a rare and fragile moment in cosmic history. Light from the cosmic microwave background still reaches us. The cosmic web still spans our sky. Billions of galaxies still shine before fading beyond the event horizon. In the distant future, the universe will not disappear, but it will fall silent. Galaxies will drift away. The night sky will grow empty, and the story of the cosmos will be hidden from all who come after. Future observers may never know the grand structure that we can see today, but we do. We are among the lucky few who live at the brief intersection of cosmic visibility and human curiosity. We can look back to the beginning and forward to the end. Our moment is not the center of the universe, but it is a window unlike any other. A moment where the universe still speaks and we are still able to listen. We are not standing outside the universe looking in. We are inside it, made from it, moving with it. The atoms in our bodies were born in stars. The stars formed in galaxies. The galaxies emerge from ripples in space-time. When we look at the night sky, we are not observing something foreign. We are watching the universe look back at itself. The cosmos does not need an outside to grow. It does not need permission to expand. It simply unfolds vast, silent and astonishing. And here we are, a brief flash of consciousness daring to measure the infinite, to name the nameless, to trace the edges of the universe that has no edge. The universe expands, and so do we.